So our next speaker is Robert Oeckl, and he'll talk about hands-on with the positive formalism. So please, Robert, the floor is yours.
Thank you. So I just want to thank you, Rick, also for organizing this. And I think it's a very useful resource also from the point of view of having archived then later the talks. And okay, so let me start. So I'll tell you about the positive formalism. I guess many of you have heard about it. And here on this title slide, I put let's say what's really the main reference for the positive formalism. And I put it here also because the title of this paper does not contain the words positive or positive formalism. Okay, just a moment.
Tanto, venimos a ver, Jair.
Es una plática ahora, ¿no?
Ya está.
Sí, perfecto. Gracias. Okay. Okay, I'm sorry about this. There was a problem with the electricity here. Okay, it seems to be fixed now. Okay, so yes, the positive formalism. So what is it? Okay, let me see if I can move this thing. Yeah, okay. So this is a predictive framework for physical theories, which is operational, probabilistic, and compositional. So what do I mean by this? Operational means that we have a primitive notion of measurement, of observation, of intervention. So instead of describing physics by saying, okay, we have a system, we have states, and now we want to see how they behave, the starting point here is the very notion of measurement, observation, or intervention. And everything else is secondary in the sense that it's built from this primitive notion in an indirect way. Probabilistic, so we are not, so we're going to predict outcomes of measurements and probabilities for them, and not make predictions that in general are certain. Okay, they are just, just probabilistic in general. Compositional means that we can talk about composing not systems, a system come later, but compose measurements, observation, and intervention. So we can say, so we measure this there, and then later something else here, and we are also switching a handle on this apparatus, and so we can compose all these notions together. So here, again, the primitive notion that encodes measurement, observation, or intervention, we call this a probe. This is basically the same notion that in other frameworks is called an operation or a process. Okay, so we'll use the word probe. So we also use a graphical representation of this framework where the probes are represented as boxes. And here, the way I drew the boxes is to indicate that they correspond to some kind of measurement devices. Or for example, this one here corresponds to a switch. This is some kind of light that can have different colors, and this is a pointing device. And now, as I said already, the boxes here represent the probes. And what we can see here is a composition of 3 probes. And we can think of this composite as a single new probe. And it simply represents the joint measurement or the joint action of all these 3 probes. So we have this instrument switched on A. We can see the green light on this other instrument, and the pointer points to a certain number here on this pointing device. And so in order to accomplish the composition, what we have connecting these probes, these boxes in the diagram are links. And so the links indicate in which sense these probes, or one way you can think about this is in which sense there are signals that can be interchanged between them, or communication between them, or an interaction. And then some more mathematical details. Let's say the links carry state spaces in which will connect later to what we know in quantum mechanics, for example, or in classical mechanics. The spaces of probes. So since we can put different probes in these boxes, we can talk about the spaces of probes. And of course, we also have the state spaces that I mentioned. And both of these types of spaces are partially ordered vector spaces. So they are vector spaces that carry a partial order. I'll say more about this later. And moreover, the mathematics behind this gives us a positive real number, or when I say positive, I mean non-negative, a non-negative real number, if we have a closed graph composed of probes and with these links. And so one key aspect of the positive formalism is, of course, how do we predict with a positive formalism outcomes of measurements or observations. And to do this, what we need is not just one of these graphs or diagrams, as we've seen on the previous slide, but in fact, we have to think about two copies of those, because when we ask for a probability for something to happen, we have to specify what we already know about our system. So for example, in this case, what we know already is that we have these three apparatuses, and moreover that this one here is the switches in position A. And the probability will be really the probability that what happens is what's indicated in the probes on the left-hand side, conditional on having the probes on the right-hand side. And so, unsurprisingly, this probability will be a quotient. As I said already, each of these diagrams, when they're closed, of these graphs, gives a number. So it's simply the quotient between these two numbers. So it's this will be the numerator, the question which encodes the question we are asking, and the denominator encodes what we already know. And here, so these diamonds are just a symbol to symbolize this composition without talking about these links explicitly. Now, there are different versions of the positive formalism. What I've told you so far is what can also be called the abstract positive formalism, where you can connect probes arbitrarily with each other. And so you just have a graph. Now, what you usually do, and for example, that's the case of quantum mechanics or also classical mechanics, you add a notion of time, and that allows you to talk about time direction of these links. And what you get is a directed acyclic graph, or directed acyclic graphs. Now, there's another important ingredient that you use, for example, in the standard formulation of quantum theory that I'll mention later. You add a causality axiom. This gives you the same kind of graphs, but what it means is that you impose certain restrictions on what kind of probes are allowed. And when you do this, your probability rules simplify. So in particular, this kind of probability rule, if you're talking about a measurement where at the end of the measurement you're discarding, and on the right-hand side here, what you're conditioning on consists only of non-selective probes, then this denominator is 1, and you recover a probability rule that just looks linear. Okay, so I mentioned a little bit, I made some allusions to quantum theory, but I didn't really say that I was talking about quantum theory, and in fact, I wasn't. So the main mathematical structure that I mentioned is that of partially ordered vector space, and in particular, these state spaces that I mentioned are partially ordered vector spaces. And it turns out they are not all the same. So if you just have, for example, a finite dimensional partially ordered vector space of a certain dimension, it will not be isomorphic in general to another one of the same dimension, but they're different types. So what are the types? So one type is called a lattice, and what happens there? Well, the state space in this case is the algebra of functions on a set. And that set is nothing else but what we usually think of as the phase space. And these functions are just statistical distributions on phase space. And basically, in this situation where the state spaces are of this type, what you can describe, for example, is statistical mechanics. And more particularly, this happens. So the framework you're in statistical mechanics is the positive formalism, this classical version, where you have a notion of time and you also have this causality axiom. Now, there's a kind of other extreme case, which is to the lattice case, which is the anti-lattice case, where this state space is basically the space of self-adjoint operators on some complex Hilbert space. And this is exactly the case where you get quantum theory. And indeed, the standard formulation of quantum theory is precisely the positive formalism in the quantum case with a notion of time, of directedness, and the causality axiom. And you recover exactly the standard formulation of quantum theory. Now you can have other situations where you don't have neither lattice nor anti-lattice, and this is then you have basically generalized probabilistic theories that are of some interest in the foundations of quantum theory. People are interested in that, and they are usually formulated in what corresponds to the in a formulation that corresponds to the positive formalism plus time plus causality axiom. Now, an example here of an application. Well, this application is the indefinite causal structure, and this is a work of Oeckl, Costa, and Bruckner from 2011, a seminal work, where they describe a situation where you have two laboratories, but you weaken some of the rules of quantum theory. And in particular, you can think of this in terms of what I was telling you as three probes, two of them laboratories, and one that describes how they interact with each other. And now you allow this interaction, which so in their formulation, it's called the process matrix, to not obey all the axioms of quantum mechanics. In particular, you are removing this causality axiom and also the acyclic directive ordering axiom. So I'm just putting this example here to say that this fits completely natural in the positive formalism and can be described in this way. And now, other directions of applications. I was, in fact, I didn't go much here on when I was on this slide. I didn't go into details about this version of the positive formalism. What you do here is you think of the probes as localized in space-time, and so you make a diagram that corresponds to space-time or to a division of space-time into regions with interfacing hypersurfaces, like here. And so now in each region you have a probe, and the interaction, what I draw before as a link corresponds to the hypersurface that interfaces these two regions. So this is the setting that's in fact relevant for quantum field theory and for quantum gravity, which I'll say a little bit more about in a moment. This is also the setting. There's a pure state version of this, which is called the general boundary formulation, which has existed much longer than the positive formalism and has been used in particular in spin-form quantum gravity quite extensively already for quite some time. Here another example from quantum gravity, black hole bounds. It's an extremely simple model that just has two parameters where a black hole transitions to white hole, so because of some quantum gravitational effects. And in terms of the positive formalism, you just have two probes here. One is the quantum evolution in the interior of the black hole, and the other one is a classical spacetime where you make a measurement. So you have an observer that sees a mass shell collapsing to a black hole, then it bounces to white hole, and at a later time the observer sees the shell coming back and can measure the time and can infer something about the exterior geometry. There's a one parameter family of these geometries parameterized by the bounce time, and then can use that if he knows how this quantum theory of gravity works, predict the bounce time. What I want to draw attention to here is that there's no definite temporal order between these two probes. So this happens at the same time. So this is why with the usual formulation of quantum theory, this is problematic and cannot really be treated. But with the positive formalism, that's perfectly treatable. So there's a paper 2018 about that. Another example, Rick, can you tell me how much time I have left, just to be, sorry. Okay, so here's an example from quantum field theory. The S matrix is where you have some initial state, separated particles, then you have some interaction, and at a later time you make a measurement and see what are the particles that come out. So this is usually done in a time interval setting. So you think of this initial state being at very early time, the final state at very late time. But it turns out that, I mean, using the positive formalism, you can do this in a quite different way and have different types of geometries. So in particular, you can think of a sphere, having your experiment in a sphere, and you shoot in particles and they come out and you detect them on a detector. So this is quite close to how actual experiments actually work. And so you model this by this hypercylinder, which is the sphere extended over all of time. And you have particles going in and coming out there. And you have a Hilbert space of particles associated with the boundary. And then you can calculate the amplitude, and you can calculate scattering probabilities using the positive formalism. And the advantage of this, for example, this also works in ADS, where the usual S matrix doesn't work. And another application that we've recently focused on is that you can use this to describe the interaction of evanescent particles with an Uno-Dewitt detector. So anyway, I'll say more about this. Somebody asks me. So okay, I'm coming to the end of this small presentation. Here's just a little presentation of our group here in Morelia. So working in particular with Daniele Colosi from the NES, also here in Morelia. Adamantia Sampelli, she was a postdoc here. She just went to ICTQT at Gdansk. We're working on measurement in quantum field theory. With Daniele, we're working on the evanescent particles, the time of arrival problem. Juan Orendine, he was a postdoc. We're working on a categorical formulation of the positive formalism. Mario Molina, he just graduated. He got his master's thesis graduated just the day before yesterday. Okay, so let me just say, so we have opportunities here for people to join on different levels, PhD, postdoc in particular, also masters, and yeah. So thank you for listening.
Amazing. Thank you, Robert.